Um, Today I am giving a topic on relation, and this comes under discrete structure and theory of logic. So in my PPT, in my lecture, I am giving what are the contents of my topics. These are the definition of relation, representation of relation, operation on relation, types of relation, and properties of relation. So in the previous lectures or videos, you have learned about the sets. So from there, the definition of relation comes. So the definition of relation is the ordered pair xy is a single element consisting of pair of element in which x is the first element and y is the second element. As you have learned in the ordered pair that x and y, these are the ordered pair. This element come under the first element, and this is the second element. So in relation, I am telling that the ordered pair xy is a single element consisting of pair of element. That means x contain in the set of A and y contain in the set of B, like the set A contain x and set B contains y. So the ordered pair of these two is known as the relation between A and B. So here I am taking, if A and B is a set A and B, then A and B containing A and B, the set containing A and B, that means B and A is also contained in the set. Like if we are telling A cross A or A cross B, that is the Cartesian product of A and B that contains x and y. So this means that one. The relation definition is that the ordered pair xy is a single element consisting of pair of element where x is the first element and y is the second element. The proper definition of the relation, a relation R from set A to set B is the subset of A cross B. That A cross B is a Cartesian product of A and B. As you have learned in the set that what are the Cartesian products. Okay, so how we are representing a relation A and B with that one. In the second point, if A and B is belongs to R, we say that this relation, this A and B belongs to R, or we can say that A is related to B. Okay, A is related to B and we write that A relate to B, that means A relate to B. And next, if the relation is not belongs to R, then what we will write, AB not belongs to R. This is the sign which says that it is related or belongs. It is not related. Okay, so we write that this is A not related to B, that is A not related to B. If we are representing A and B which is not in the relation, so this is the representation. A is not related to B, or A is not related to B, that means A is not related to B. If A and B, A and B are same, then we say that relation is related to A cross A. It means the element of A is equals to, like A equal to 1 2 3, and we are saying that A equals to B, B also contain 1 2 3. So it means A is equals to B. So we are showing that relation is related to A cross A. It means A cross, that here I am A cross A, it means the Cartesian product of A cross A. It means 1 1 1 2 1 3 and so more. So it is showing that A cross A is a relation on A. There is an example, A equals to 1 2 3 and B equals to XYZ. So the relation is 1 Y 1 Z. You can take any one. A2 related to B. So we are saying that our relation A is related to B. Okay. So with respect to this relation, 1 is related to Y. Here I have written, sorry. So here I have written it, 1 is related to Y. Here you are showing 1 is related to Y, 1 is related to Z, and 3 is related to Y. Here I have written it, 1 is related to Y, 1 is related to Z, and 3 is related to Y. But 2 is related to 2 is not related to X, 2 is not related to Y, and 2 is not related to Z, that I have written here. This is the proper definition of relation. So here comes the next topic, domain and range. The definition of domain is, the domain of a relation is that the set of all first element of the ordered pair which belongs to relation that is denoted as DOM of R, and the range is defined as, the range is the second element of the ordered pair which belongs to R, which is denoted by RAN of R. Okay, this is the easy where I have to tell how to find domain and relation. So here set A contain 1, 2, 3 and set B contain XYZ, and consider the relation here given a relation of set A and Y, that is relation 1Y, 1Z and 3Y. So how to find the domain and the range of this relation? So the domain, as I have given the definition as the first element of the ordered pair which belongs to R. So this is the first element 1, so this comes under the domain. Okay, this is the relation 1 also again come here, so we will write one single times. If there is a multiple times over there, we have to write only 1. Okay, and 3 is another unique number, so 3 also come under the domain. And as range I have defined the second element of the ordered pair. So the second element was is Y, Z. Okay, so the range is Y and Z. This is clear. Okay, next topic, how to represent our relations. There are 4 types to represent our relation. First is relation as a matrix, second relation as a directed graph, third relation as an arrow diagram, and fourth relation as a table. There are 4 types to represent our relation. Our first type comes under a relation as a matrix. As I am telling you, relation as a matrix, how to say it, the relation, the P means the set P contains A1, A2, A3 and AM, and Q, B1, B2, B3 and Bn are the finite sets containing M and N number of elements respectively. R is related from P to Q. Here I am saying that there are 2 sets and given a relation. How to represent it in a matrix form? There are given an example where the set P 1, 2, 3, 4 and Q A, B, C, D, and the relation is given 1A, 1B, 1C, 2B, 2C and 2D. There is a relation here given it. So we have to we have created our matrix form like P has 1, 2, 3, 4. We have written 1, 2, 3 and 4 like this. 1, 2, 3 and 4. Okay, and Q A, B, C, D, A, B, C, D. Now the relation has given 1A. The relation which has given, we have to mark 1 on that one, otherwise we will mark 0. Okay, so the relation has given 1A, it means 1A, here we have marked 1, 1B 1, 1C 1, 1D, there is 1D is not present in the relation, so we will mark 0. Okay, 2A, there is 2A, no, 2B yes, 2C yes, and 2D yes, otherwise there is not given for the 3 and 4, and that's mean it will be marked as a 0 for all. That I have made over here, you can match it. 0 1 1 1 0 0 1 1 1 0 0 0 0 and 0 0 0. This is the way how to represent our relation as a matrix. Now the second topic is relation as a directed graph. There is another way to represent our relation by the directed graph. Here is a set has given a 1 2 3 4 and relation 1 2 2 2 2 4 3 2 3 4 4 1 and 4 3. So this is the set 1 2 3 4 and this is the relation have given over here. So we will mark 1 2 3 4 there. We will put 1 2 3 4 in the any side of corner 1 2 3 4 you can mark it. And now how to make as a directed graph? Here is the relation 1 to 2 1 to 2, okay, 2 to 2, it means it will be a self loop, okay, 2 to 4 2 to 4, again 3 to 2 3 to 2, 3 to 4 3 to 4, 4 to 1 4 to 1, 4 to 3 4 to 3 and 4 to 3, okay, and 2 to 4 here over here, also over here, okay. This is the directed graph. It is easy, there is no confusion about that. There is a relation over given to you guys and you can make as a directed graph. Now next, relation as an arrow diagram. If P and Q are finite set and R is a relation from P to Q, relation R can be represented as a diagram. I have taken an example. Let P has the set is the finite set and Q also a finite set and relation is also given over here. 1 to A, we will make as an arrow diagram by the making 1 2 3 4 as a P and this is the Q, okay. So 1 to A again, 2 to A 2 to A, 3 to A also, 1 to B also, 4 to B also, and this way you can make your relation as a arrow diagram. Now the last type, relation as a table. It is same as relation as a matrix, okay. I have taken P and Q as a set, finite set, and R as a relation. So how we are representing our relation as a table? We have created table 1 2 3 4 and XYZ, 1 2 3 4 XYZ and XYZ and K, okay. So we are making the relation which has given, we will mark cross over here, otherwise we will leave blank. The relation which is not given, we will mark blank, otherwise if the relation has given, then we will mark as a cross mark, okay. 1x 1 to x, so 1x there we have marked x, okay. 1y we have marked x, 1z here not given, so we have left over here. So this way 2z 2z 2z, 3z 4k. So like this we can represent our relation as a 4 type. I have taught you, represented as a matrix, represented as a directed graph, represented as a table, and represented as an arrow, okay. You can make your relation as these types. Now next topic is operations on relation. So there are 3 operations on relation: union, intersection, and difference. So the definition of union of that, given two relation R1 and R2 is defined as the union and it is denoted by RU R2, R1 U R2. U means union, okay. If A and B is belongs to R or it is related to R1 and R2, that is means it is union, okay. So the formula of R1 union R2 is AB, such that AB belongs to R1 or AB related to R1 and AB belongs to R2 or AB belongs to R2, okay. R1 union R2, that means AB related to R1 or AB belongs to R2. You can make this by operations by Venn diagram also. If there is a numerical over given here, how to find union of A and B, the set have given and the relation has given, you can make it, okay. The relation have the union. And the intersection means we define the intersection of the relation by the R intersection R2, that means AB, which AB belongs to R1 and AB belongs to R2, that means R1 intersection R2. And the definition of difference is that we define the difference R1 and R2 in a given manner, R1 minus R2, which shows that AB, where AB is related to R1 and AB is not belongs to R2. Here I have written R1 minus R2 equals to AB, such that AB related to R1 and AB not belongs to R2. These are the formulas, operations on the relation where you can use it and you can solve your numericals. So I have took example of for solving the numerical for union, intersection and difference. So set A as 1 to 3 and set B is U and V. Okay, and the relation has given R1 1U, 2U, 2V, 3U, and R2 is 1V, 3U and 3V. So what is R1 union R2? R1 union R2 comes that all the elements, which means you have to make all the elements present over here, R1 union R2, like 1U, 2U, 2V, 3U, okay, 1V, 3U has given, 3V also, like here 1U, 2U, 2V, 3U, 1V, 3V. Okay, this is the R1 union R2. I have not written 3U here, it has given because it is repeated. That's why I have not given that one. Means the element which is present in both the relation, it is union. Okay, now the intersection. The intersection part is that which is present in only the both. Okay, so R1 intersection R2, 1U no, 2U no, 2V no, 3U only 3U. So R1 intersection RU is equal to 3U. Okay. Now difference, I have told you difference that the relation in R1 present, AB is present in R1 means which is related to R1, but it will not relate to R2. It means 1U, 2U, 2V, 3U and 1V, 3U and 3V. It means 1U is not related to 1U is not related to R2, so it will be in the R1 minus R2. R1 minus R2, it means R1 have present but not in R2. It means R1 minus R2 having 1U, 2U, 2V. Okay, and R2 minus R1, 1V, yeah, 1V, 3U, no, 3V. R1 minus R2, it means we will check the elements present in R1 but not in R2. R2 minus R1, it means the element present in R2 not in R1. Next, types of relation. Okay, the first type is identity relation. As I have wrote, identity relation I on set A is a reflexive, transitive and symmetric. So identity relation is an equivalence relation. Identity relation means it is related to itself. Okay, the example I have given, set A 1 2 3, the relation is 1 1 2 2 and 3 3. 1 1 2 2 and 3 3 is also comes under reflexive, symmetric and transitive. That's why I have written it is an equivalence relation. Void or null relation means the element it is given that R such that A to B such that R is equal to, there is no element in A cross B, that is null relation over here, that is not in a symmetric and transitive and not reflexive. Means null relation, you can show that by this one, that is a null relation. Universal relation, a relation R AB such that R is equal to AB is subset of A cross B is a universal relation. It means AB is a reflexive, symmetric and transitive, so this is an equivalence relation. I have took an example, set A 1 2 and set B equal to AB. The relation I have given 1A 1B 2A 2B. It is an universal relation because it have given the elements present over here, all the elements 1 2 also and AB also. So it is a universal relation. Okay. Now inverse relation, it is an important relation over here. It means R in if you have a set A and set B, the relation is just opposite. RA, it means AB present in RA, then R inverse equals to BA. Okay, if a relation I have given a set AB and CD, the relation BA and DC. Okay, I have took a relation in set A, AB and CD. The inverse of relation is AB and DC. Okay, this is inverse relation. Now, properties of relation. There are three properties of relation. First is reflexive. There are many types of reflexive: irreflexive, symmetric, antisymmetric, asymmetric, transitive. Okay, first is reflexive. Reflexive relation. A relation R on set A is to be a reflexive if AA belongs to R and every A is belongs to A. It means here I have took set A 1 2 3, then the relation is 1 1 2 2 1 3 2 4 3 3 3 4 4 4. Is the relation is reflexive or not? It means for every AA is present over here, it means it will show the relation is reflexive. So check over here, the element of set A, it is related to itself or not. 1 1, yeah. 2 2, yeah. 3 3, yeah. 4 4 also over here. It means this relation is an reflexive. I have written in the solution, for every A 1 1 2 2 3 3 4 4 belongs to R. So this relation is a reflexive. Okay, irreflexive, the a relation R on set A is said to be irreflexive if AA is not belongs to R. For every A is element, it means the element which is not related to itself, it is irreflexive. So the example over here, the set A 1 2 3 and the relation over given here 1 2 2 2 3 1 1 3 is the relation R is reflexive. So the solution is that AA is not belongs to, it means you can check 2 2. Okay, so it is 2 2 is over present over. The relation is not reflexive but for every element of A, but if it is not reflexive, so 1 1 3 3 also present over here for reflexive. So it is not reflexive. So what we can say that it is irreflexive. Okay. Now symmetric. A relation R on set A is to be symmetric if AB belongs to R, then BA also belongs to R. The equation and the relation of saying that only and only if, okay, a relation A R on set A is said to be symmetric only and only if AB belongs to R, then BA is also belongs to R. The set A has given 1 2 3 and relation 1 1 2 2 1 2 2 1 2 3 and 3 2. So we have to check this is symmetric or not. So we are checking that all the element, if 1 1 has given 1 1 2 2, these are the identity elements. So identity relation, so it will present over here. Okay, now we will check 1 2 2 1, yeah. AB BA, good. 2 3 AB 3 2 BA, yeah. It means it is satisfying the symmetric relation. So it is a symmetric relation. Okay, but it can be reflexive when 3 3 is also present over here, but 3 3 is not present in that relation, so it is a not reflexive. Okay. Antisymmetric. A relation R is said to be antisymmetric if AB belongs to R and BA is belongs to R. AB belongs to R if and only if BA belongs to, then A equals to B. Okay, if A and B belong equal, they are equal, then it is a antisymmetric. Like A equals to 1 2 3 and relation have given 1 1 2 2. So it is antisymmetric or not? Yeah, equal. And if A B is not in the antisymmetric, if A is not equals to B, then also we have to check B is not equals to A. Okay, for antisymmetric, if AB is present over here, then BA is not present in that one. Okay. In antisymmetric. Asymmetric, a relation R is said to be asymmetric if and only if for every AB belongs to R, that implies BA does not belongs to R. AB present over in the relation, but BA is not BA not belongs to R. Then the transitive. A relation R is said to be a transitive if and only if AB belongs to R and BC belongs to R, then AC is also belongs to R. There is an example over to check whether the relation is transitive or not. Set A 1 2 3 and the relation is given over here 1 2 2 1 1 1 2 2. So we have to check whether the relation is transitive or not. So the relation R is transitive for every, it means 1 to A B and this is BC, it means AC has to relate, okay, to 1 1, it is present over here. Okay, so this is a transitive. As I have written in the solution, the relation R is a transitive for every AB and BC belongs to R. We have AC belongs to R. So through this we can check whether the properties of relation are satisfying or not. We have read there are many types of properties. First we have read reflexive, it means AA belongs to R. Irreflexive, AA does not belongs to R. Then symmetric, if and only if AB belongs to R, then BA also belongs to R. Okay. Antisymmetric, AB, if A equals to B, then AB belongs to R, then also BA belongs to R. If there is another condition, if A is not equals to B, okay, then AB belongs to R, then BA not belongs to R. Then asymmetric, asymmetry, here we have learned about that AB belongs to R, then BA does not belongs to R. And in the transitive, AB belongs to R and BC belongs to R, then AC also have to belongs to R. These are the 6 properties of relation. Now using this property we are learning about the equivalence relation. As we have in the previous slides, we have learned about reflexive, symmetric and transitive. So we are through using these properties we are checking whether the relation is equivalence or not, and it is important for all. So how to check the equivalence relation? Okay, for equivalence relation the definition is given as equivalence relation on set A is a relation which is reflexive, symmetric and transitive. There are 3 properties which contain in the equivalence relation: reflexive, symmetric and transitive. So as we have learned about in the previous slides, R is when the reflexive, it means A is related to A, and in symmetric A is related to B, then B is also related to A for every element for belongs to A. Okay, and the transitive, A related to B and B is related to C, then A is related to C. This is the definition of equivalence relation, but the proper is that equivalence relation on set A is a relation which is reflexive, symmetric and transitive. A relation R is defined on a set is said to be an equivalence relation if and only if R is reflexive, that is, which I have told, A related to A for all A belongs to A. Second, R is symmetric, that is A is related to B and then B is related to A for all AB belongs to A. And third one, R is transitive, that is A related to B and B related to C, then A related to C for all ABC belongs to A. Okay, so if these 3 properties holds for any equation, and then that relation or equation relation, it is called as an equivalence relation. Okay, now whether I have took an example, check whether the following relation is reflexive, symmetric or transitive. There is a many examples over here, but I have took one and I will make another one also. For relation, there is a examples over here are 1 2 3. So we are checking whether the following relation is reflexive, symmetric or transitive or not. So for one, our relation is given 1 1 2 2 3 3, okay, 1 3 1 2 2 3. So the set A belongs to 1 2 3. As I have forgotten to put it over here, but relation is given 1 2 3. Okay, so we are checking hana ki R is reflexive, symmetric or transitive or not. For reflexive, this is the formula. If A related to A, for all A belongs to A, it means A belongs to R. Okay, this is clear. So we are checking if the set A has given 1 2 and 3. So for reflexive, it should be relation should be present 1 1 2 2 and 3 3. Okay, so if 3 all are present, then the relation is reflexive. So we are checking these 3 elements, these 3 present are not ordered, but 1 1 2 2 and 3 3. Okay, these 3 are present for all, so this is a reflexive. Okay, now for this relation we are checking this is a symmetric or not. Okay, for checking the symmetric, symmetry, okay, we will check A is related to B and then B is also related to A. So here we check 1 1 1 3. So 1 3 1 1 1 3. Okay, AB and BA. Okay, 3 3 1 also present over, no, so this is not reflexive. For symmetric 1 1 1 3, so 1 3 is, this is transitive. Okay, 1 1 2 2 3 is present, so it is reflexive. There is not symmetry, and for transitive 1 1 1 2, so that is 1 2, yeah, it is present, so it is transitive. So for this we will do, and thank you for this one.